morning, everyone. This is Dinesh R, who is going to present about the importance of FEA and why we need in this real-world application and how it enhances our performance of the overall usages in our industry. So the thing is, why we need FEA? So let us take any object in the nature. It's continuous in nature. How I can say it is continuous is, for example, if I give you a chalk piece or a material, you can break it into two and then 4, and it will continue up to 16, 32, and it goes up to infinity. So this is how they state the material are continuous. But our particular tool, our finite element analysis tool, divides the continuous object into finite number of elements and assigning a nodes to that, and also a governing equation of motion to solve the any problems like static or dynamic or vibrational setups and etc. So today we will take up one problem where you will be seeing a finite element analysis on assessing the conditions of crank arm, and also we'll see the overall interface of SolidWorks simulation application, so that you will get the overall insight of what is happening around the SolidWorks simulation, how user friendly it is. So first you will see what is FEA and its use in assessing the durability of the material. So this is what you are going to assess today. You can see over crank arm over here. So it's a bicycle crank arm. So initially, if you go to purchase any products like electronics or any manufacturing products, you will be given a warranty card. If the material fails within that, you can take advantage of that and claim the product, a fresh piece. So after seeing this much of products, and the customer end have come to a conclusion that we should use a durability tool to assess its overall cycle, so that we can ensure our market sustenance and also our customer satisfaction. So I will just show you. So we have taken n number of crank over here. So you can see the failure over here. So repeated number of cycles it has been subjected, and after some time it get failed, and also you can't bring it back, weld it or anything, but we have to accept the failure. So in order to assess the failure in advance, we use this FEA tool. So material strengths and the fatigue cycle. So the material strength is a separate thing. If a material is sustaining a static load of something, the same cannot be applied to the durability. 95% of the material in manufacturing sectors fail due to the fatigue failures. So you can't assess the same with what you do in the static analysis using a yield strength, but you will be using the SN curve over here, and we will be assessing the failure of the analysis of your particular part. So to assess the same and showcase the what is happening inside the SolidWorks FEA and also any solver, we have taken 3 designs of crank arms. So design 1, design 2, and design 3. So here you can observe that we have 3 design, and we don't know which is the most optimal design, and also which can sustain the more desired number of life cycles. Okay, so these are designed using a SolidWorks CAD, and we have given the material as applicable. So we are giving a static load of initially and checking its factor of safety, and we are observing the factor of safety or within our industrial factor of safety, and we are designing for a maximum cycle for that. Minimum cycle should be a 7 million. In order to achieve the same, I am importing all the crank arm configuration, all the 3 crank arm configurations into the SolidWorks FEA. So here we will be you will be assigning the material and import the material, and also we are going to mesh it, and we are applying a SN curve over the material, and SN curve take advantage of that and apply the conditions and give us the result. How much life cycle it could withstand, and also the damage tolerance which we have given. So on assessing that, we have given that initial design has been running on the durability cycles of 4 millions. But the maximum stress, which is having a yield strength of 275 megapascal, which is within the factor of safety 1. So the maximum deflection which I have achieved is also 4.3. So the minimum on the cycles doesn't satisfy the desired fatigue life cycle for my component. I desired for 7 million, but the cycles which I have seen satisfied was only 4 millions. So I will be jumping on to the next design. So in the design 2, I am applying the same thing, same static load, and I am taking the load into our fatigue analysis, where I am applying your design standards and also SN curve to get the overall fatigue life and also the damage done to the part. So the life cycle which I have observed is 14 millions, which we have more than that desired fatigue life. So which crank will last more? So I am doing the same procedure with the third one and the third design. And the third design have been seen at yield strength of 275, but my observed maximum stress is 250, but the minimum factor of safety is more than 1, and also the maximum deflection has been found to 1.8. Even deflection is minimum, but I can observe that fatigue life cycle to be 1.3 millions, which is very less when compared to our desired fatigue life cycles. So that's the thing which I have to make a concern of. So even though I am designing with heavy material and also the perfect design, but out of the 3, I am observing that only one design of me is satisfying that particular life cycle of a material. So I am declaring my second design stage, and I am just analyzing one prototype, and also I am releasing it to the market. So if I am an FEA analyst, I would rather prefer the design 2, which has a more fatigue life cycle and also give a good results when it launches into the market, and also it satisfies the customer, which is my prior most important. If you are not satisfying the customer, I can't sustain in the market. So my prior most important would be this particular one. So okay, these are the theoretical part which you have seen, but when jumping into the FEA and how our SolidWorks FEA, without knowing that we can't do the further analysis, right? So we will see a simple simple static analysis using our FEA and how FEA functions, and also SolidWorks FEA functions. Let's move into SolidWorks FEA now. So I have created a simple extruded rectangle over here. I'm just going to do a static analysis of the particular part to assess its overall failure, and also how much deflection it has went through, and what is the conditions we initially record. Any FEA tools like ANSYS or Abacus or SolidWorks FEA records these 5 steps. So the first one would be importing the model. So in SolidWorks, it is not at all a concern for us. SolidWorks FEA has an in-cab capability to use the CAD modeling simultaneously. So I'm just importing it to simulation, and we are going to run only the static analysis, where the force won't be changing with respect to time. So the first step we have completed. Moving on to the next step, we have to assign a material. So I'm just assigning a plain carbon steel, which is a mild steel, known as known in a marketplace. And the thing is, we can observe the elastic modulus, Poisson's ratio, and mass density yield strength highlighted in the red. So these are the four prerequisite properties for running any yield static analysis. The yield strength shows how much it deflects when it given axial tensile load. And so the Poisson's ratio, the lateral strain by longitudinal strain, and also the mass density, the how much it is tightly packed, and the yield strength, the place or the phase after which the point at which the plastical deformation of the material starts. So I'm just applying the same and just giving OK. So moving on to the next one, I'm just applying the fixture over here, giving the fixed over there. So when coming to fixture, we can see the each part can be constrained in 6 degrees of freedoms maximum. So 3 in the rotational and the 3 in the translational. So if I click on the fixed geometry, it will be in all the 6 degrees of freedoms will be constrained. If I am clicking on the roller, it will move along only its plane, and the inch it will be along its rotating along its axis. So I'm just giving a fixed constraint over here. So now next coming to the step 3, which is a boundary condition, and the fixture also, connection also, external loads all comes under this particular step 3, the boundary condition. So I'm just applying the force over here. I'm giving the reverse load of 1000 kg, so which is 10,000 Newton. So here you can observe the force, torque, and also the non-uniform distributions. When it's like hydrostatic, you won't be using a uniform pressure condition. So at that point, you will be using the non-uniform condition, where you can assess the hydrostatic pressure and what happens to component when it is subjected to the hydrostatic pressure. So meshing, the meshing is the most important part, which discretizes the part. The part which is continuous in nature can be discretized over here. So I'm just creating the mesh over here. So here you can observe the mesh parameters. So it is blended curvature and curvature based and standard mesh. I'm just going with the curvature based mesh. When it is like a caching part, you can go with the blended curvature based mesh. So I'm just giving the default mesh quality should be on the higher, since Tetra 10 is a higher quality element and Tetra 4 is a lower quality element where you don't have any mesh side nodes. So I'm just giving OK. I'm just meshing. So you can observe the mesh over here. So after meshing, the only part we should consider doing is our mesh quality check. So if you go onto the part, the summary over here, you can observe that study name as a static. And so the Jacobian points, 16 points, and the maximum and minimum elements. So that are the consideration you can see there. And also the most important thing is your aspect ratio, which is a maximum element length by the minimum element length, which you can observe it as a 99.5% of the element passing the test, which is a good sign for any analyst who are performing the static or any basic kind of analysis. If it is greater than 10, it is a worrying sign. You should work on that. You should minimize element size or do a mesh control on a critical regions. And the percentage of the distorted elements. So distorted elements never gives an accurate value. So we have to make it as a oriented element in order to function it properly. So in this problem, we don't have any other concern like that. You will be running the analysis as required. So this part, you can change the units over here. So I'm observing 12 megapascal pressure, which is well beyond my factor of safety. A factor of safety is nothing but yield strength by maximum permissible stress. So I'll just include the force limit over 10,000 kilogram force. I'm just observing 121 megapascal of pressure over here. So I'm just going to see whether it is within my factor of safety, the desired factor of safety or not. Okay. So my factor of safety is 1.8. So this is how you can assess the failure of the material. So whether it is within our desired factor of safety, and the material, when it is subjected to the prolonged and on and off loading like fatigue loads, you can use the same and you can assess the failure of the material using the S1 curve. So these are the important points which I have to mention from my end, how the FEA of our SolidWorks functions. And if I go to the stress analysis parts, you can see more number of stress interpretation, result interpretation, where you can see that material, it depends upon the material. If I am using a ductile material, I would rather go for a one measure stress or a maximum energy distortion, maximum distortion energy theory. The one measure is a person who has formulated that, so that when a yield material fails, we have to incorporate the same. So if it is a principal stress theory, when you are using the brittle material, you would follow the same. So over here, you can also check for the hotspot diagnostic and also the resultant force over here. And I'm checking the design intent plot. So the design intent plot shows how where the material is more loaded. So what is the critical region of the material? So what can be the condition which we can give or improve so that we can eliminate the portion in order to achieve a good results. So these are the things which I have to mention it from the SolidWorks FEA, where you will be using the inbuilt InCAD simulation tool, which is very useful in analyzing the structure and also its overall fatigue analysis tool. So these are the 5 steps which you go to any solver, you will be using the same and also incorporating the same in order to execute that. So I'm just going to recall the things which we have seen today. So this is how we have started analyzing the crank arm by taking a normal FEA tool, our SolidWorks FEA tool, and we have analyzed the crank arm and we have taken the 3 designs of the same and we have left with the options of 3 and we have chosen the best one basis on its number of desired cycles, which is more than our expected one. So here the maximum stress which has been induced directly affects the fatigue life. More the stress and more the failure is. So this is how you can incorporate the same in your organization as a FE analyst or a senior design engineer or a design engineer or a manufacturing engineer, industrial engineer. You can apply the same and you can give the output which could be fruitful for your organization, and also it can help implement the same in your R&D team. So that's it from my end. If you have any queries regarding a SolidWorks FEA and also the FEA and how to use it, you can contact us. This is Dinesh signing off now.